Tommy, you want me to go ahead and get started then?
So I just opened up. Attendees are now joining in. So let's give everybody about a minute to get situated with their audio, and we'll begin from there. So I'll give you an update.
Yeah, just let me know.
Yep.
Boris, you like myself, you like to collect paper, hard copies of things and put them in your bookcase rather than everything's PDF.
Don't tell me. I got some really great books. In fact, maybe I'll show some of those. I got some. A colleague of mine, Claudio Tomagnini, told me about this bookstore in Paris that sells original, well, of course, copies of originals from Lagrange, from people like that. And I have those up there, and I have some old ones from my school, and I even have, my dad was an engineer, so I have some from his. I have original Gauss tables from early century, last century, and I have to show it to students here because they all just have computers and they don't know. I said, well, what do you think? How was it done before? Oh, it wasn't done. I said, no, it was done. Look around you. So then I had to show them these things just to No, I love these. I keep them here. I don't know what I'm gonna do. You should see me at my home office. My God, it's.
Yeah, eventually. With PDFs, I managed to organize a little bit more. Otherwise, I would have been stacking stuff on the floor, I'm sure, like everyone else. But it's hard to pass up getting good hard copies.
Oh yeah. No, I love
it. All right, gentlemen, whenever you're ready, Jim, we could start. You could do an introduction for the webinar. I'll just quickly before we start say that we are going to give about 50 minutes or so to our presenter. No questions during the presentation. We'll wait to the end. You can write questions in the chat or the Q&A that we'll take in order after the presentation, and we'll open up the microphones to anybody that wants to have a one-to-one chat after the presentation. So with that, Jim, if you would like to begin by introducing our speaker today.
Okay, well, good afternoon, everyone. My name is James Rickles. I'm the PI director of the Lehigh NHERI multi-directional NHERI experimental facility. And today we have a speaker, Professor Boris Jeremić, who I'll introduce here in just a moment. But before that, I want to mention this is a seminar series that provides opportunities for the audience to hear the trending research that's going on in the natural hazards field, provides opportunities for the presenters to market and demonstrate their added value to the stakeholders. And also it serves a purpose to market our own facility, who basically pursues research and supports researchers such as Boris to do their research. So having said that, we're very fortunate to have Professor Jeremić today here. He's going to talk about epistemic and aleatory uncertainties in numerical analysis of earthquake soil structure interaction. And let me just say a few things about his background before I hand the podium over. Professor Jeremić obtained his civil engineering diploma degree at the University of Belgrade in Yugoslavia. And following that, he has his Master of Science and Doctor of Philosophy in Civil Engineering, both at the University of Colorado in Boulder. Now, his research interests, I know he has many, but his primary research interests are related to modeling and simulation of static and dynamic, inelastic, deterministic, and probabilistic behavior of civil engineering objects. So I guess that's just about everything there. Now the focus is on the development, and more importantly, as important, should I say, the use of these methods that reduce modeling, epistemic uncertainty that can propagate through the parameters of an analysis, including the aleatory uncertainty. I'll let Professor Jeremić explain all those details. So I also want to mention he has a number of technical papers and reports, and these are available through his website. And I think in the end, probably you'll show that website, or we could put that up on the concluding page. So with that, I'd like to welcome Professor Jeremić, and I'll hand it over to you, Boris. Thank you.
Thank you very much. Thank you for inviting me. It's a great pleasure to be here to present. Actually, if there's one good thing that, well, few things came out of COVID. One of those is we learned how to use Zoom. And so this is a positive count for COVID, at least something. Anyway, thank you very much. So yes, as Jim said, I have many interests, and I'll run you through some of those today. So the idea is really to talk about these modeling and parametric uncertainties in our modeling. I'm interested in soils and structures and earthquakes. This is done over many years. Over the last few years, main contributors were Dr. Han Yang, Professor Han Yang. He's now professor in China in Tianjin. Dr. Heshen Wang, he's now working for Warren Buffett, so he can probably buy us all. And then Dr. Sumit Kumar Sinha, he's now professor in Delhi. So with that, I'll just go straight ahead. And the main interest really is to improve or to give engineers tools to improve safety and economy of infrastructure objects. We want to actually be able to improve the analysis, because at the end, everything is a model, and we need to decide on shapes and materials we use to design those objects and to assess their behavior. So we would like to improve the analysis for those objects. And really the interest is in both statics and dynamics, but one of the most serious types of loading is earthquakes. And this applies to both soils and structures. In my view, there's no difference. You need to know soil, you need to know structure. You cannot separate those two. There are essentially two main types of uncertainties that we have to deal with. The first one is what I call modeling uncertainties. Some of my senior colleagues tell me, well, it should be really called epistemic. And I agree, okay, fine. If people know them as epistemic, that's fine. So but these are really modeling. I'll spend some time on those. And then of course, there are aleatory, there are parametric uncertainties. Our materials are variable, they're very uncertain, and we need to take that into account as well. Our goal should be to predict and inform. We should be predicting and informing the audience, the engineers, because engineer needs to know. Engineer needs to know good news, bad news. Engineers need to know what is going to be the behavior of objects so that they can do what they need to do. They can improve them or change them or sign down on at the bottom of design drawings or not sign at the bottom of design drawings. The easy stands for earthquake, soil structure interaction. Challenges are very similar for many different objects. For soils, you always have the seismic wave field propagation through. So number one is seismic wave field. Number two would be propagation through the soil, and then number three would be interfaces. That's actually a very important part of the behavior. Number four would be the actual structural behavior, and then number five would be fluid. And it's very similar for free field behavior, for interaction with some structures. Some important, some less important. They're all important, but some of them are very important, like nuclear power plants. Some of our buildings, and then of course dams and bridges. It's a very similar set of modeling tools, analysis tools or similar challenges that we need to address. The two main types of uncertainties are really modeling uncertainties and parametric uncertainties. When we make those models, usually finite elements, we do make simplifications. We simplify life or simplify models because there's no way we can model every single atom and so on. So we go from particles to solids and then to structures. But we need to be able to change modeling sophistication level so that we have a good confidence in our results. And then once you decide on the actual level of confidence or level of sophistication for your model, you have to propagate parametric uncertainties. Our components of our system are very uncertain. Mostly stiffness, but also viscous, damping, part, and mass. They are uncertain. The loads are also very uncertain, and so we need to be able to propagate those uncertainties through the equations, through our behavior. And we would like to have the results be full probability distributions for everything, for displacements, velocities, accelerations, for stresses and strains, pretty much everything. And I'll show you we actually do that. So let's focus a little bit on the modeling uncertainties. We have to sometimes simplify some of the important features. We used to have to do those. We don't have to do that anymore. There are tools, there are good tools that actually you don't need to simplify those out. And so, for example, the issue of one component motions versus three component motions. And I used to use 1D, 2D, 3D, but my French colleagues remind me that actually this is for geometry. 1C for one component, 2C for two component, and 3C for three component. And then I also added the 6C because anytime you have three translations, you will also have some rotations. They're going to be coming from traveling waves and whatnot. So 6C is a good way to say it. And then of course we sometimes simplify our systems to elastic, and there's no such thing as elastic system. They're always inelastic. Let the system decide if the soil structure system wants to be elastic or inelastic. So those are some simplifications we make. If you make a simplifying assumption, simplification in your system, it is a good thing to be able to go 1 or 2 levels of sophistication higher, just to demonstrate that your simplifications are not affecting results too much. And how much is too much? It's up to you. It's up to the engineer to decide, is 1%, that may be pushing it, or is it 50%? That may be pushing it on the other side. So it's up to the engineer to decide what is the level of simplification that he or she will allow in the system so that the results are useful, because you need to improve safety and economy. Once you decide on the level of sophistication, you have to deal with the variability and uncertainty in material and loads. And I just pick up, this is from famous paper from K.K. Foon and Fred Callaway from a long time ago, from 24 years ago. This is what you use in geotechnical engineering, for example, based on SPT, the sun penetration test. How do you decide Young's modulus? Well, there's an equation. There's the only way you can fit this red line through this cloud of points is if you use Excel. I don't even know how will you do it by hand. I guess you can fit any line through this cloud of points. But if you show this line, that given by this equation here, it's a good thing to also show the residuals, because to show what's the actual distribution, because that gives the other side information that, well, this might not be very certain piece of information. And once you do that, and of course there are other uncertainties in the system. Once you do that, it's also important to realize that our loads, in this case earthquakes, are very uncertain, and that needs to be taken into account as well. So let's talk about some of these modeling uncertainties. I still call them modeling because that's close to my mind, but I understand they're epistemic. That's what they're called in mathematics circles. So, for example, do we use solid structure interaction or do we not use solid structure interaction? Well, there's a difference. There's sometimes significant difference, sometimes not that significant. It's important that the engineer can show what the difference is and maybe neglect the influence of soil, but we can do actually much better nowadays. Do we do one-dimensional models, two-dimensional, three-dimensional models? We can do nice three-dimensional models. Sometimes it doesn't make a difference, but you will not know unless you actually are able to do three-dimensional models. Seismic motions, I'll show a few examples. What if we just use one component motions? What does it do to our results? Are our results good enough for design and for assessment? Elastic versus inelastic behavior. Again, material is always inelastic. Let the material decide if material wants to plastify or get damaged and so on or not. Let's not decide instead of material what models to use. And then, of course, I'll briefly mention energy dissipation, because most of the damage we have and most of the problems and most of the behavior of soils, for example, and for structural damage happens because of energy dissipation. There's a trend to actually use viscous damping to model this energy dissipation. That is not quite right. Physics of viscous damping is very different than physics of inelasticity. So it's appropriate. It's important to use appropriate models for appropriate physics. In terms of ground motions, ground motions are always three-dimensional, three-component ground motions. We know from theory, we measure those. We know that we have primary waves and secondary waves. We know that they result in surface waves, Rayleigh waves, love waves, close to surface, layers right next to the surface, Stoneleigh waves. We know that from theory, and we do measure those. And yet we sometimes, or a lot of times, we neglect those. So again, most motions are full three-component motions, three translations and three rotations. And I give the two examples. There's a famous motion from Lottum. This is LSSD07, I think 1986. The one on the left side is actually a very special motion because it has a very, very little up and down. The lowest one is up and down. The upper ones are east, west, and north, south. And so this actually tells me, and if you look at the actual downhole area, you can see that the actual wave was almost plain wave propagating vertically. There was no inclination. And this is one of the rarest motions I've seen. Exactly same location, different source. A few years later, resulting in a wave field on the right side. And you see there's a full up and down. And that the first part, remember, the first couple of seconds of up and down are essentially just the P wave. And then after that, it's a surface wave. So again, we know that motions are mostly six-component motions, three components, plus three rotations. We need to be able to model those. So I'll show you a simple example we did just to demonstrate this. Let's say that you assume that we have a full three-component motions, but we only record one component. We just pretend that only one component is recorded. And then we can use that one component and do deconvolution and propagate back as a one component motions. And this is how it looks like. This is a simplified model we did just to demonstrate. Again, it's a very simplified model. It's sort of, you can think of it as a regional scale model. There's a point source, which again is not quite true, but just it serves the purpose. There are layers. There's a rock layer. There's a little stiffer layer of soil, and then a softer layer of soil. And the location here you see on top where that line is, that's the location of the object. It's not an object, just a location. But we can see that these motions propagate, and we see the reflections and reflections through the layers, and we see how this is what we also observe a lot of times when we measure those motions. If I go close to this object here, let me see how this looks like close to the object. This is how it looks like. Please note that there will be a lot of these surface waves, and these are Rayleigh waves, the ones we teach students. These are the same ones we actually record. So now, if I use these waves, this realistic wave field, it's a very simplified source, but very realistic wave field. I can actually input that into my model, my free field model, and this is how it looks like. This is input in the free field model using domain reduction method Jacobo Bielak invented about a little over 20 years ago. It's a beautiful method, the best method to input motions in any model. So this is how it looks like in real life. And then if I do the one component motions, this is how it's going to look like. I took those motions at the surface, and I just said I pretended they're just one component motions. Let's see how the system behaves, and it behaves like this. So the left one is the real motion, the right one is the one that is one component motion that we most of the time actually use. And I would say that the physics is different. I would say that physics between the motions on the left side and the motions on the right side is quite different, and I expect to see different behavior. How important that difference in behavior is, well, I can show that too. Here's an important object. Let it remain unnamed. It's a full 3D model, but what we did in post-processing was to actually take the left side, and the left side shows the full three-dimensional motions, the 6-component motions, including rotations. The right side includes only those one-component motions, and you'll see the difference. It's a very different behavior. The left side has a lot of these vertical motions that they come from the actual Rayleigh wave, from the surface wave. The right side does not have those. So again, the behavior is going to be quite different. And then I get questions, which one is on the safe side? Well, you can't say that. I mean, the safe side is the one on the left side, because the one on the left side shows realistic motions. The one on the right side shows unrealistic behavior from unrealistic motions. So I would always take the more realistic behavior, because that helps me as an engineer to decide about the shapes and materials and so on for my object. And then, of course, we can, again, the issue of wave fields, what kind of wave fields we use in modeling. So let's look at those so-called stress test motions. In addition to these realistic motions that come from some depth or from some real earthquakes, which we developed by essentially doing regional scale models, or, now we actually have a methodology that by using some surface measurements, we can actually develop a full wave field at depth, and we can propagate that back in there. What we can also do is we can propagate some analytic wave fields. There's a set of papers by Thomson, and then there's another set of papers by Haskell from 1950s. 1950 Thomson and 1953 Haskell, where they provide closed-zone solutions for layered media for the inclined wave, and we use that to input through DRM into our model. So here's an example of a wave field. At 1 hertz, a very long wave, at 2.5 hertz, at 5 hertz, and 10 hertz wave field, very short waves for 10 hertz, and you can see how they look like. And they have a very different behavior on the surface. So, for example, in this case, the 10 hertz wave field, you see now this is a model that's about 300 meters by about 200 meters in dimension. And if I have an object on top on the surface that is that has a dimension of 50 meters to maybe 100 meters. The actual behavior of the object is going to be very different. I cannot apply one component motions, because those one component motions are not going to excite properly rotational parts, and the vertical parts that you see here are really the surface waves, not the P wave. So it's important to be able to model this and then to learn about the actual behavior of object. Here's that same wave field, the one that I showed before. Now we actually have a deeply embedded object inside. This object is about 40 meters embedded. And it's about 25 meters wide. It's an SMR, small modular nuclear reactor. And you see the actual behavior at those higher frequencies is actually very different what you would observe if you apply them as one component motions. And of course, the wavelength is going to make a difference depending on the size of the object. And so your object might not even see some of the waves depending on the stiffness, of course. But this is important. Those high frequencies become very important for industrial objects. So behavior can be very different, and you need to be able to model that. In the last few years, people say, well, but we can actually do 3 times 1 component. They call this 3D motion. It is not. The 3 times 1 component is really just you do the convolution of 1 component, second component, and third component, but they're all 3 components in one component. And so you see the left side is the real motion, the real wave. The right side is the one that is 3 times 1 component. Behavior is quite different. So it's important to be able to do this properly. And then, of course, the big discussion, should you use SSI or non-SSI? Well, soil is always down there. It's just, you can't get rid of it, soil or rock. They say if it's a very hard rock, you don't need to. Well, there are differences, sometimes more significant. If it's soil, the differences are always significant. This is an example, the Ventura Hotel, famous hotel in Southern California, that was shaken a few times, and we did a simple. We did an elaborate model of this hotel, and we did a SSI and non-SSI model, and we compare with some of the motions that they were recorded, and the full SSI model does really well. The non-SSI model doesn't do well. You can fiddle with parameters, you can do this, you can do that, but it doesn't do well. So the conclusion is that you need to do full SSI just to get the good behavior of models. So the energy dissipation. The energy dissipation is important because that's what brings damage to our systems. And we can calculate the energy input using DRM, and then we can calculate different ways of dissipating energy in the system. And there's a radiation damping that we know about that, but then there's also all sorts of energy dissipation and conversions inside the SSI system, and those are really important because they are the ones that bring either settlement in soil or some slippage in soil or damage in structures. And so we need to be able to model those properly. And of course, there's one component that is rarely taken into account. It's numerical damping. Whenever you use Newmark or HHT or any of those methods to integrate in time, you dissipate energy. In the system numerically. You can even produce energy, and that you need to be able to control that. And this is important to control. And we can control that. We have a way of controlling. We have a way of analytically calculating energy dissipation at every single Gauss point, every single finite element, and we can plot those and we can show what they are. And then, of course, engineers should be able to go back and forth and learn about where the energy dissipates and what's the influence of numerical damping, what's the influence of viscous damping, how to choose those parameters. That's important. One really important note here is that the plastic energy dissipation is not the same as plastic work. The stress strain loop is not plastic dissipation. My applied mechanics colleagues know this, and I remember when I talked to one of the colleagues across the hall, he said, of course, everybody knows this. I realized this maybe 10, 15 years ago, and I was shocked because I thought that the stress strain loop or low displacement loop is actually plastic dissipation. It is not, it's plastic work. There's something called a plastic free energy that's missing. And this was shown by a fellow named Jeffrey Taylor 100 years ago. He has a series of papers starting in 1925, I think the last one came in 1934. They did some tests on copper. He showed this, and applied mechanics people know this. Civil engineers are not very familiar with this. This is important because you get, how did I learn about this? Well, I did some tests and I wanted to convince myself that what I do is right. And then I plot and I see there's a negative dissipation. This can't be, thermodynamics says this cannot be. So I spent 2 years trying to figure out what's wrong, and I learned about these work. And so plastic, the loop of low displacement loop and stress strain loops are not, the surface area of those is not plastic dissipation. We can calculate plastic dissipation very accurately. So one of the issues, of course, always is should we use elastic? And then we say we over design, and then we say we are on safe side. Maybe not so. There are ways to show that you're not on a safe side if you over design. But one of the things, for example, if you use elastic and inelastic, actually inelastic can help you. And inelastic is going to dissipate some of the energy down in the soil and some of that seismic energy is not going to propagate through the soil. But you then need to also take into account that there will be additional settlement, and you need to be able to model that. And you need to be able to take into account that additional settlement in order to make sure that your object is functional after an earthquake. Because if you settle more, for example, for nuclear power plants, there are some things called umbilical cords, the connections with, power and water and whatnot. You need to make sure that they can take a little extra deformation. So being able to do this properly using inelastic response material, soil and structure both, and especially the interfaces, is very important. And then, of course, you can look at the energy dissipation and use that. So this is that same power plant that is dissipating energy for the most part in those interface elements. And you see here, this is cumulative on the lower left side, on the lower right, in the middle is the actual incremental dissipation. You can see that a lot of that dissipation happens, and you can actually use to your benefit, the actual structure will not see most of the energy propagate because of the tiny slippage that happens between the foundation and the soil. Again, this is something that is sometimes observed in some of the objects. They survive better than they were expected to survive some of the earthquakes. And for the most part, the reasoning is that there was a slippage down at the bottom. You might end up with a little bit extra settlement, but there's a slippage, and then that prevented all that energy from going through the system. So this is important. This has to be properly modeled. And again, we can do this, and I won't go into much detail of this, but if the object is deeply embedded, like that SMR, that small modular reactor I was showing you, you see that, for example, most of the dissipation happens in the close to surface where the actual confinements are low, the slippage part, and then the other part of dissipation happens at the bottom where the actual soil is very compressed, but soil is going to plastify a lot. And so again, you have to be able to properly follow the actual energy through the system. And then maybe change shapes and change materials, maybe weaken materials. This is the story when we do the, when you put the actual energy dissipators in the system, base isolates also, you're essentially controlling where the energy goes. You can then, of course, use that to change design. So here's a simple frame. This is a standard pier frame developed many years ago. And this frame, now you have a choice, for example, for foundations. If I have two types of foundations. The foundation, the slab on the right side, dissipates much more energy in the interfaces and in the soil. And so what happens at the end, as you'll see that the actual and I on purpose showed to show the same scale, the coloring scheme is the same for both of those. So you see a lot more dissipation in soil and interfaces, and then you look at the structure. There's a dissipation here in these corners, but there's also dissipation here as well. If you look on the right side, there's quite a bit less dissipation in the structural components. We actually have numbers. We show this by numbers, but just by judging by colors, a lot less dissipation because, of course, it's a different static system. This is a little stiffer down at the bottom, but nevertheless, a lot of the dissipation happened in the foundation. The actual seismic energy did not propagate through the system up to the structure, so this structure on the right survived much better. Again, this is important. In last few years, we got involved with ASC 7, the new revision. You note here that it's 21. I'm not sure if it's out yet. It's always late. The BRB, the buckling restraint braces, you can use them to dissipate energy. That's exactly what the idea is. And so you can use them. And so then you see that actually, you can design the structures that can actually dissipate energy where you want the actual energy to be dissipated. One interesting observation about this was that some of the structural colleagues told me that they were always, it's a 3-field set of BRBs. They would always just subdivide into 1/3, 1/3, 1/3. It turns out that in this case, remember, whenever you plastify, there will be redistribution of loading. In this case, the two side fields take most of the loading. The middle field does not actually take that much loading. And so this is an interesting observation from a high quality, high-end modeling of a system that non-linear system, soil structure system. So again, the point being that you need to be able to do proper modeling with proper level of sophistication, both structure and soil, and decide the behavior of the system. Once you do that, of course, you need to go back and address the other hard issue, and that is the parametric uncertainty, the aleatory uncertainty. We know that our components are uncertain. The material is variable. We don't know exactly what the numbers are, what the material parameters are, so, you know, for mass, it's fairly certain. Viscous damping is kind of uncertain, but for stiffness, it's very uncertain. And the loads are very uncertain. So we need to be able to address that. So, you know, so what we started doing some years ago was, you know, given uncertain material and given uncertain loads, what is the uncertain response? How is the actual response of the system going to look like? And instead of using Monte Carlo, which is kind of, I shouldn't say simple, but it's much simpler than what we did. You know, but Monte Carlo has many inefficiencies. Monte Carlo is slow and it has a slow convergence to very accurate solutions. And so we wanted to skip that. And we actually used the stochastic finite elements, the ones that Roger Ghanem and Paul Spans developed three decades ago. But we extended those into allostoplasticity. So we actually now have so-called stochastic elastic plastic finite elements. It's a so-called intrusive approach because we actually go inside and we change our finite element equations, and the system becomes very large, but it's orders of magnitude faster and more accurate than the actual Monte Carlo. Here's what it does. Essentially, we have a simple elastic plastic incremental equation. All of these components inside become uncertain, including the actual strain. And then all this uncertainty goes back to the actual finite element system. And, you know, simplified, just to demonstrate what this means, let's say you have a simple elastic linear hardening material. Your deterministic solution will be starting from 0. Material is going to go here, it's going to yield, it's going to continue with this red line, and this is your response. Once you decide that you want to have uncertain elasticity and uncertain plasticity, your response is going to become uncertain. Your response is not going to be a single set of points, you know, stress strain or a single line. It's going to become a distribution. So in this case, distribution will have its own mean. It's going to have its mean, and then its own mode, the most likely outcome. It's going to have plus minus sigma, plus minus some variation, but it's going to be a full distribution. And you know, this is what we wanted to do. This is what we are doing currently. You know, for example, you know, a lot of people know about Chem Clay model, very simple but beautiful, elegant model that actually only works for monotonic loading. The interesting observation here is that, you know, your deterministic line, your deterministic predictions are away from the mode line, from the most likely outcome. And it can flip and flop up and down, which means that your deterministic solution, of course, depending on the parameters and uncertainties in G and, you know, the shear modulus and the slope of the critical state and the P naught, the previous highest confinement, depending on the uncertainties in those, you can be on the safe side or you can be on the unsafe side. And that should make a difference. That can make a difference in your decision-making process. So again, I'm not going to go into details. I'll just show briefly. So these dynamic finite elements, the stochastic elastic plastic finite elements, we take the input random field of the material, we take the input random process of the loads, and we expand those in multidimensional Hermitian polynomial chaos. And you know, we essentially are developing those input variables, the multidimensional Hermitian polynomial chaos with unknown coefficients, and it's a complete probabilistic response. One important thing about this approach is that you do not need to define intensity measures. All of the probabilities are inside. The probabilities of material, the probabilities of input motions, they're all inside. You do not need to decide on intensity measures. You do not need to make any choice. So here's an illustration. So here's a simple, very soft cantilever with some nodes. And what I'm showing here are the actual 50th percentile, the mode. It's a symmetric distribution in this case. So it's a very simple cantilever that is behaving elastically, essentially. And I hit the top, I move the top, and the wave starts to propagate downward. And what I'm showing on the right side is the actual fragility, the fragility of the displacements of the top node. And you see that they dynamically change as the wave propagates and as the system shakes. But I actually have a full information about every single node. I can plot fragilities or probability density functions for every component of this model. And based on that, I can make some decisions. This is giving me far more information than if I had to choose some intensity measure and then I just pick up one component and then I have to run few of those using Monte Carlo. In this case, I get the full probabilistic response. So where is this applicable? Well, for example, let's do a simple example of seismic hazard. You know, in California, we are lucky or unlucky that we have a lot of earthquakes. So there was a lot of work on earthquakes, and so we have We have, we have the so-called U-surf maps. We have a very good knowledge about faults and about the rates of slip and whatnot. And so we can use that to develop some motions, and we can develop a characterization for those uncertain motions for some location. Then we can go through the uncertain material, and we can go through stochastic, elastic, finite elements and develop a full uncertain response. And I'll show you an example. And then, of course, later on, we can develop full hazard risk for any component, anything that the engineer decides to do. So in this case, let's do a simple example. This is a site. This is some location. This is actually downtown San Jose, a little bit south from where I am right now. We pick up two faults, San Gregorio fault and Calaveras fault. And we know from those user maps, we know what the uncertainties are. We know the segmentations, we know slip rates, we know rupture geometry. I mean, we know about the uncertainties. I mean, and they're significant. You'll see they govern this response. And then what we can do, we can generate a large number of those seismic scenarios, and then we can use those to actually to generate stochastic ground motions, which we then analyze stochastically, probabilistically, and develop characterization of those motions through polynomial chaos. And once you do that, of course, then you decide on your object. In this case, it's essentially a one-dimensional shear beam. It's a structure that has a very stiff interstory, the panels. And so we essentially provide some uncertain response, nonlinear inelastic response of those interstories. So it's essentially a 1D model. And so this 1D model, and you can of course extend this to soil beneath and so on. We load up that model with our uncertain loads, our uncertain earthquake from beneath. So it's uncertain loads and uncertain earthquakes. And then, of course, what you get at the end is a full probabilistic response. We get full probabilities in each time step for all the displacements, all the velocities, all the accelerations, all the stresses, and all the strains. And then you can go inside this wealth. I mean, these are really large data sets that come out of this, but you can go in and just pick up whatever your heart wishes, whatever your soul wishes to look at. So in this case, we picked up a maximum interstory drift. And we can do that at any time instance. So in this case, you can see how they change from 15 to 21 to 29 seconds. Of course, from that, you can do the fragilities for that, the annual exceedance rates. And then, of course, you can do that for every single floor, for first all the way up to the top floor. Again, all this information is available from this approach using stochastic elastic finite elements, and you did not have to decide on intensity measure. It's all inside, and it's all inside the results. Of course, the input is very significant, and the output is even more significant, large. But you have all the information that you need to decide on your object. Of course, you can do more. In previous slide I showed just the interstory drift. You can do more because again you have everything. You can, for example, go for peak floor acceleration, and you also have information about that. And again, information about that for every location, for every finite element, for every node, and you have information of that for every time spot or for every time point. And you can do that. And then what you can actually do, you can combine those, because you have a full probabilistic response. You can then do marginal probabilities. You can combine those and look at probabilities of maximum interstory drift versus peak floor acceleration. And then actually you can define your damage measures on a single engineering demand parameter. Like in this case, what's the risk that you're going to have more than 0.5 interstory drift, or that you're going to have more than 1%, 2%, or so on, or what is the actual risk that you're going to have more than certain number of the acceleration for certain story. But you can actually combine them. You can define multiple EDPs, and you can now combine them. You can show, for example, what's the probability of having either 1% initial drift or 1 meter per second acceleration, or what is the actual probability that you have both at the same time, the second one. And you can then define seismic risk based on some of those. So again, this is something that is very, very powerful in this approach, because it gives engineers a lot more power, a lot more good information about what is going to happen with the object. And so these risks defined on multiple EDPs can actually be quite different from risks that's defined on a single EDP. Now, having said that, one of the things I've been thinking about for the last almost, well, actually 20 years, was, okay, so we have these input parameters, input uncertainty parameters. How do we decide where to spend time and money? And colleague Norm Abrahamson told me this 15, 20 years ago. He said that when they decide on free field motions, depending on who is deciding on that, who is in the room where decisions are made, somebody is going to push hard for the actual, looking in details at the actual sources and path, the earthquake down at depth, at rock site, at the depth in the rock. And then some other groups might actually push hard for the actual soil. What is the actual site response? And there was really no good rational way of deciding which way to go. Now you can actually look at sensitivities. Given forward uncertainty response, the PDFs and CDFs I just showed, what are contributions of uncertain input to those forward uncertainties? In other words, for this site response, for example, what is the influence of the uncertain earthquake at the depth, the rock at the depth, and what is the influence to final uncertainties? What is the influence of the site uncertainty, the uncertainty in soil parameters? So you can actually do the sensitivity to the input parameters, and that's actually something we've been doing for the last 3-4 years actually, by using Sobol indices. Very powerful methodology developed by Sobol, Ilya Sobol, some 20 plus years ago, and then but he did it using Monte Carlo. Then even really important work was done about 12 years ago by Bruno Sudre from ETH in Zurich, where he combined the polynomial chaos, the same polynomial chaos that we use for forward propagation. You can actually use that polynomial chaos, those extensions, for the backward propagation for the sensitivities. And based on that, we actually have these Sobol indices, Sobol sensitivities. So here's a simple example. At this example, we have also the uncertain earthquake. It's one of the scenarios or uncertain scenarios, the probabilistic scenarios. And then we have a soil profile. We have some simplified soil profile, and we know what the uncertainties of those material parameters are. And we did this simple example just to show how this works. So for this particular set of uncertain earthquakes and this particular set of uncertain soil, again, we use the same user for some site. And again, it's somewhere in downtown San Jose. We use those stochastic motions. We do expanding polynomial chaos, and we use probabilistic DRM, the same DRM that Kogubielak developed. We now do it probabilistically. And then we actually do probabilistic forward propagation, and then we do sensitivity study. And we get the actual, for example, again, we have a full response, so we can look at the sensitivities of different demand parameters, and we can look at different damage measures. And so in this case, we decided to look at the PGA, the P ground acceleration. And so in this case, for this particular case, again, this is important. This is going to be different for different cases. For this particular case, this site for these uncertain motions, 49% of the uncertainty on the top PGA comes from the uncertain rock motions. Only 2% from uncertain soil. Now, of course, there are combinations. So there's a combination of soil and rock. The uncertainties of both soil and rock, that comes also at 49%. But in this particular case, if I was to decide where to spend time and money, what to characterize better for this particular site, I would get a much better result, much less uncertainties in my final PGA in this case, if I spend time and money on the actual rock motions. The soil is uncertain, but it's good enough. It's good enough. It's uncertain, but it does not contribute that much to the final uncertainty. What contributes most is the actual rock motion depth. So in this case, we actually have a rational way of deciding what is the influence of input uncertainties to the final uncertainty. So again, in that sense, this is very new, and this is very I'm very proud of this. This is actually something I've been trying to do for many years. Again, this all works in just one component, 1D. We're now working on 3D 3 component, and this might be coming, well, a few years, maybe more than a few years down the road, because it's hard to do this in 3D. So in summary, again, I'd like to strongly emphasize the need to address engineering analysis uncertainties. Engineers need to know this. They need to be able to address both modeling epistemic uncertainties and parametric aleatory uncertainties. This is really important to be able to address both, so that you as engineer have good confidence in your results, and you have good confidence in your designs and in assessment of objects. Again, engineering analysis is there to predict and inform. If I cannot predict and inform, if I have to fiddle with some parameters just to fit a curve, I'm not happy with that. I don't like to do that. I'd rather predict and inform. As engineer, I need to know. I need to know, and is it good news or bad news? If I cannot predict and inform, something is not right with my modeling, something is not right with my analysis, I need to improve that. I need to go back and improve that. I do not like to fiddle with parameters just to fit some curve by using wrong models. And all of this that you've seen is actually done using our program, Real Easy Simulator. There's a website here. And all these models I showed and all these examples are available through this website. And there's a link to my lecture notes and so on. And you can download those models. You can download the program. You can download executables and run them today. So again, the main point is to be able to design sustainable objects, to design long living objects so that they live longer than we do. And that's good. So I put a few examples down here. The Hoover Dam actually is the youngest of these objects here. It's only close to 100 years old. Hagia Sophia is 1,500 years old. This Ctesiphon, this arch, actually in Iraq, is 1,000. I think more than 1,500 years, maybe 1,700 years old. This bridge in China, down south from Shijiazhuang, is 1,500 years old. And the Brooklyn Bridge is about 150 years old. We would like to be able to design objects that can live this long and just serve their purpose. So with that, I'll thank you for your attention, and I'll take questions if there are any questions. Thank you.
All right, thank you, Boris. Yeah, we'll open up for questions. I see some coming in the Q&A, and then or in the chat. And then if anybody would like to speak, you can raise your hand in your participant list. On the bottom bar of Zoom, you'll see a raise hand icon if you'd like to talk. Okay, so.
Yeah, I don't see those questions. Can I stop sharing my screen so I can, I can share
absolutely,
again?
yeah. I mean, if you would like, you're able to open up the question and answer and start that discussion on your own. I don't need to redirect those questions.
Okay, so chat.
Please, yeah, read them out loud for us.
I don't see them in chat. I see
in Q&A. If you would
okay, Q&A. Okay, I see. So Ahmed, when I click on Ahmed, nothing happens. Hold on, let me do Q&A again. Oh, I see. I'm sorry. Yeah.
Great.
Indeed. Thank you very much for the presentation. Could you please talk more about what is the computational cost of the stochastic finite element method? And will the cost increase with the larger number of uncertain inputs? Yes, the cost is large, but it's less, a couple order of magnitude less than Monte Carlo to get the same accuracy. And yeah, so you end up with much larger system, because what you essentially do, you take every single degree of freedom and you expand those degrees of freedom into polynomial chaos, into uncertainty eigenspaces. And the system becomes much, much larger. But again, it is more efficient and much more computationally efficient than Monte Carlo. So in that sense, you're right. It is more computationally intensive, more costly, but it's better. It is cheaper and more efficient, cheaper and more accurate than Monte Carlo. Second question. Amin. Hey, Amin. Hello. Thank you for your presentation. I have a couple of questions. I'm not sure if I agree that the material randomness is an aleatory type. Well, epistemic. Okay, so yes, and we do this game. We play this game of moving the border between aleatory and epistemic. Yes, it's epistemic if you have enough time and money to go down and drill and get all the material properties. But we don't have enough time and money. So what we have to do, we have to move that into the epistemic part, the parametric part, because the aleatory part, because in that case we have good mathematics to deal with randomness, and we don't have good physics to deal with the actual finding all the properties down. I see your point, and you're right. But we decide to move that into parametric uncertainty, so that we can deal with that numerically. G. Wang Connelly, can you please explain how engineers can use the information such as PDF of interstory drift? Should certain percentiles be used? Yes, I mean, once you have a full PDF, full probability distribution function for anything inside your system, for any displacements, any acceleration, any velocity, any stress, any strain, any component of stress or strain, it's up to you to you can come up with percentiles. You can integrate it. You can get the fragilities. You can get CDFs, and it's up to you. It's up to you. But you have all that information available, and then it's really a post-processing part that you pick up some of that and post-process them. You can combine them. Again, it's up to the engineer to do that and to do post-processing and choose use any of that information and do the post-processing. Anonymous attendee, is SEPFM available in public? Does it have 2D, 3D, or just in 1D? So SEPFM is within Real Easy. It's available in public. You can download the executables or you can run it on Amazon. The SEPFM is only available in 1D right now. We have a number of proposals and we've been working on it for the last many years into 3D. It's kind of complicated. We hope to have some 3D results soon. Well, soon again, give me a few years. You can download Real Easy and all of that is available. And if you go to the website, there's a link to my website and there's a link to documentation. There are examples and documentation and the input language and all that kind of stuff, and you can download those examples and just try them out. So again, SEPFM is only in 1D currently. It's available through the program and you can run some of those examples. Everything else is full 3D. Let's see. I mean, again, another question. What is your definition of fragility in your presentation? So fragility is the CDF, is the integral of the PDF. Yes, the standard definition is probability of reaching to a specific limit state condition on uncertain stressor. My definition is really it's a cumulative density function, and this is essentially the integral of PDF, and it can be any of those results that you have inside. And so the stressor will be the uncertain loads, the uncertain motions, and in this case, the uncertain material is going to behave the way it wants to behave, and then you can look at any of those probabilities of any displacements, velocities, accelerations, stresses, and strains. And then you can look at them at every time instance, every time step. You can look at those, and then you can decide how you want to post-process that. So again, it's quite a bit more information that you get, and then I guess what we have to do is we have to learn how to post-process that. I mean, not technically, we can do that easily, but how to understand such wealth of information, how to use it to our benefit, as opposed to just defining an IM in the beginning and then looking at some interstory drift. You have everything at your disposal. You can do any combination of these or look at any output. And one thing to do is to learn how to use such wealth of information properly. Okay, so there's Gia Van Connell again. How are the percentages of sensitivity in the example collected for the? Oh, so essentially we have the CDF. We have the fragilities. Oh, I'm sorry. You're talking about the. I'm sorry. You're talking about the Sobol indices. Well, so again, there's a whole theory behind that, and there will be a paper coming out soon. I can send you contact me. I can send you those papers, and if you go into those lecture notes that I published also on put it online, you can see some more. Essentially, you do this is based on Sobol spaces, the Sobol sensitivities, and again, take a look. There's quite a bit more theory behind that. But for some of those uncertainties at the surface, the PG, in this case, the PGA, again, peak ground acceleration. So it's going to be a single PDF. The uncertainties in that single PDF are going to be 49% influenced by the actual uncertainties of the rock motion, 2% by uncertain soil profile, and 49% by a combination, because with those indices you get combinations of soil profile and the uncertain motions. But again, it's clear from this simple example that the unknown motions of the depth govern mostly. I'm sorry. Yes, I mentioned CVs and I'm sorry, too much coffee today. Correlational length, yes. very important. So correlation length is essentially inside the system. When you look at sorry, when you look at the actual uncertainties of the material, you have a correlation length, spatial one, and when you look at the actual uncertain seismic motions, you have a correlation length in time, and those are essentially they're defined by looking at certain data, the data that you have about the soil, and the data that you have, all the motions that you have access to, and that you do probabilistic analysis to get. So the correlation length is in that correlation length information is in that data, and you can extract that as well. Irfan Alvi, do you envision that artificial intelligence, okay, that's actually might eventually be able to help deal with models of epistemic uncertainty? Some of the uncertainty seems more qualitative and not amenable to being treated as parametric uncertainty. Yes, that is true. We've been looking at AI recently. Again, I'm a big fan of computers and but it's a little scary what AI can do, what ChatGPT can do and whatnot. We've been actually teaching ChatGPT to use real easy and to give people to give them feedback if they ask question or if they do a model, because the input language we use, the real easy DSL, it's a language, and ChatGPT can deal with languages, and so that language actually, and we have a good manual on that. And so ChatGPT can go in and find mistakes in people's input files and suggest changes, just like it does the same thing for when you supply some text. I think there's a lot about AI that is happening really fast, and I'm very excited about it, to tell the truth. I think it might be able to do it, but what we're doing right now, we are learning how to influence ChatGPT, how to teach ChatGPT what to do. And this is a good point. One of those might be a good way to teach the system what about these uncertainties. Which ones are more qualitative and some are more, qualitative. So again, this is an excellent point, but I don't have an answer. I mean, maybe a year from now, maybe we'll have more answers about that. Alejandro Veri says the use of synthetic ground motions defining the frequency domain Fourier amplitude does it not introduce the Aleatory uncertainty in the generation of PDFs or different EDPs? Yes, but if you take a lot of those, so for example, you go to peer database and you download everything that's available. So this is pretty much all the motions that are available to people. You essentially you download the full motion, the full time history, and then you process that, and you get the actual probabilistic characterization of those motions. And maybe that's the reason that we actually see that such large influence of motions at depth. Because remember, there's an ergodic assumption there, and those are essentially picked up from all over the world. So of course, that is why they are so uncertain. So with new so-called non-ergodic, I don't like the term. I don't think non is a good thing to start with. I say site-specific motions, we might actually get a little better. We will actually we might get a little less influence of motions and maybe a little more influence of this uncertain soil profile. But this is a good point. Yes, you do, because these are you pick them up all from a site, from peer database, and they're essentially from all over the world. Amin has another question regarding your modeling uncertainty. My understanding is that you described in a beautiful way, thank you, different modeling choices. Okay, I'm not sure if we can call them uncertainty as opposed to choice alternative. Okay, because you did not combine them to come up with a single response. You did not combine them. I'm not quite sure, because we actually did not combine them to come up with a single response. So yeah, you're right. So they're introducing uncertainty, they're introducing error, they're introducing uncertain response, because I neglected 2 components out of 3 components. And so how are they introducing, or how are they influencing my result? That's why I call them uncertainty. There's actually a nice set of papers by Charbel Farhat and Christian Soaz from France. Charbel is from Stanford, where they look at this. They're actually trying to quantify the modeling uncertainties. I think that Ghanem also has a few papers on that. Modeling uncertainties, they're trying to present them as random uncertainties, and they actually can get some really nice, beautiful analytic results on what's the influence of those modeling assumptions. If you email me, I'll dig out some of those. I think I have them here. Thank you. Yeah. Zayad Khalil says, can you give more details regarding propagating of epistemic uncertainty in the PSH signal characterization to those of modeling choices assumptions? As a logic tree is usually used in PSHA, what is the approach you recommend to combine both? Well, in this case, we essentially take all the possible motions and we do stochastic characterization and we do the uncertain material. So you do not need to go through any of the logic trees or anything like that. You essentially have all the uncertainties in the system. For 1D wave propagation. Currently, only 1D wave propagation we can do. So again, this is the answer, that we essentially try to actually skip this part where you have to make choices, because choices introduce uncertainties, introduce errors, and they can be sort of subjective. Sorry, we try to make them objective, and we try to analyze all the uncertainties. And then, of course, at the end, you give the engineer a lot of power. And then, of course, the engineer has to make a choice of what to look at. But again, hopefully with time, engineers are going to learn to look at not just interstory drift or peak ground accelerations or peak floor accelerations. They're going to learn to combine those in different ways, for different types of structures, and maybe use one or the other or the third one, or maybe combinations of those and any other uncertainty. Alejandro, thank you. Yeah, okay, clear answer. And then next one is by, I can't slide down. Oh, I have now. Oh, Makti. Hey, Makti, hello. Dear Boris, thank you for your presentation. It was great seeing you. Yes, thank you. I don't see you, but although it was only a 2D view in 1C voice, yes. I hope all is well. I must go now. Yeah, okay, thank you. Thanks, Maki. Yeah, good talking to you. Or give me a call on these days. We'll talk some more. Let's see. How do I go down more? I guess that's it. I guess so, Jim, I think those are all, Tommy, I think those are all the all the comments, questions.
Good. You moderated your own webinar really well. So
thank you very much.
Yeah, I figured that would be easier. Yeah. And so Jim, if you just want to final comments and wrap up, that would be great.
Yeah, so thanks, Boris. I guess what we can do, if anyone has any other questions that come up, they have a way to contact you, right? They can.
Yes, yeah. So again, that website, the website has, the realeasy.us has, it's easy to find me. There's no issue with that, and my emails are there. So again,
okay.
Thanks a lot for the opportunity. This was great.
No, I wanted to thank you for wanting to give this. I think it's a topic that's very important, and it's gaining more traction, especially in the soil structure aspects. It's becoming very important that people recognize the value of this. And so with that, I wanted to thank you again and remind people that we archived the presentation. I guess we had to get your permission to
yes,
post
of course.
the recording
of course, yes.
Our website, so people can go back and catch up on things there. And with that, I guess we should close the seminar and remind people that if you have an interest in doing research like this, we have resources at our facility. We're open source, open to the community research facility funded by the NSF, that we can provide resources for people to do their NSF research on, and also help develop research proposals they could submit to the foundation. Okay, so with that, Boris, again, I want to thank you, and I think it was a great presentation. I learned quite a bit, and I'll look forward to seeing you soon there.
Thank you.
Okay.
Thank you.
Thank you.
Enjoy your afternoon.
Thanks.